The greatest impact in the history of the solar system may be hidden on the Moon. On the far side, there is a crater so large that it takes up nearly a quarter of the Moon's hidden face. It's called the South Pole Aitken Basin and spans about 2,500 kilometers across. This crater is one of the largest and oldest known impact structures in our solar system. Formed more than 4 billion years ago, it holds signs of a violent event that reshaped the lunar surface. However, what fascinates scientists most is what lies buried beneath it. Recent studies have uncovered a gigantic metallic mass hidden under the crater. This mass was detected through gravitational anomalies picked up by orbiting probes. Scientists believe that this mass could either be the core of the asteroid that hit the Moon, or the result of dense minerals fusing together at the moment of impact. The concentration of this mass is so great that it distorts the gravitational field of the area and affects the path of any spacecraft passing nearby. This distortion, known as a mascon, requires adjustments to the trajectories of lunar probes. It was this very anomaly that led to the discovery of the structure. Since then, the region has become one of the most studied spots on the Moon. Apart from the buried mass, the crater itself provides clues about the Moon's deeper layers. The impact excavated materials that would normally be unreachable, and the rim of the basin contains rocks that may have come from the Moon's mantle. By collecting samples of these materials, scientists would be able to study the internal composition of the Moon without needing to drill deeply. This is one of the key goals for future robotic missions. The impact also left visible seismic scars in several areas. Some of these geological faults can still be seen in the latest satellite images. The nearly circular shape of the basin suggests that the asteroid struck the Moon at a relatively low angle. Such a collision would focus energy in one area, helping to explain the depth of the crater. The asteroid is estimated to have been tens of kilometers wide and moving at over 50,000 kilometers per hour. The heat produced by the impact was intense enough to melt large volumes of rock. This created seas of magma, which eventually solidified over time. In orbital spectrometer analyses, the composition of this region is different from the rest of the surface, indicating unique chemical reactions caused by the impact. Some of the material ejected during the impact may have travelled hundreds of kilometers, possibly even leaving the Moon. Fragments of this debris might have fallen to Earth as meteorites. The crater also contains areas of permanent shadow near the South Pole. These regions never receive direct sunlight and have temperatures below 230 degrees. It's believed that these areas may contain ice that has been preserved for billions of years. This makes the region even more interesting, with both scientific potential and future mission possibilities. Even small amounts of frozen water could be a valuable resource for future lunar exploration. However, the terrain is not easy. Local gravity varies, the illumination is irregular, and the soil is unstable. Despite these challenges, space agencies like NASA and CNSA are studying ways to land probes or robots there. The aim is to gather more precise data about the metallic mass and the exposed rocks, and perhaps even collect samples directly from beneath the surface. If the buried material is the asteroid's core, it might contain metallic alloys that have never been accessed before. These metals could give us valuable insights into how planetary bodies form in high-energy collisions. The presence of rare elements like platinum or iridium might also reveal unknown aspects of solar system history. In that way, the Moon acts as a preserved archive. The impact could also have subtly changed the Moon's orbit and rotation. Small shifts that occurred over billions of years could have affected phenomena like Earth's tides. Some models simulate these possibilities by comparing lunar data with Earth's geological records. While there is no direct evidence, the hypothesis is still under consideration. There are also signs that the heat from the impact formed minerals that aren't found anywhere else on the Moon. These materials crystallized in unique ways due to the extreme conditions of the event. Their spectral signatures help track the ejected material, and in some cases, scientists have been able to trace meteorites found on Earth to specific points in the Aitken Basin. Despite all the studies, much of what lies buried there remains a mystery. The combination of extreme impact, hidden mass, and preserved structure makes this crater one of the Moon's most puzzling regions. It may also be one of the most important areas for understanding the violent past of our solar system. Lunar dust has a strange property. it can spontaneously explode into microbursts of plasma. The surface of the moon is covered by a fine grey powder called regolith, which forms from the constant bombardment of micrometeorites. This process has been happening for billions of years, as the moon has no atmosphere to protect it. As a result, the surface is covered with sharp, dry and reactive particles. But there is a stranger behaviour related to this dust. During the lunar sunrise, radiation begins to shine directly onto the surface. Without air to dissipate electric charges, the regolith starts to gather static electricity. This build-up can become so intense that some particles actually lift off the surface and levitate. This phenomenon, called electrostatic transport, was predicted by scientists and partially observed by probes. But it's not just dust that is affected. Under certain conditions, regolith can generate small plasma discharges. When the potential difference between particles reaches a critical level, a sudden release of energy causes microbursts to spread across tiny areas. In lab simulations, scientists have replicated this effect using artificial lunar soil samples. They believe that on the actual moon, the effect might be even stronger. These electrostatic explosions are too small to see with the naked eye, but on a larger scale, they can affect how dust moves, accumulates, and interacts with surfaces. This is important for space missions. Solar panels, sensors, and visors could be affected by the adhesion of charged dust. Even without wind or weather, the lunar environment is more dynamic than previously thought. Ultraviolet radiation plays a role in this process. When it hits regolith grains, it helps release electrons, changing the charge of the particles. This process is different from what happens on Earth, where the atmosphere blocks most of the sun's radiation. On the moon, exposure is constant, especially during the long lunar day. This creates a scenario where particles are always electrically charged. During the Surveyor mission in the 1960s, a faint glow was observed on the lunar horizon just before sunrise. At the time, no one knew the cause. Today, scientists believe that the glow was due to the electrostatic movement of dust. As the sun rises, millions of particles briefly lift and reflect light. It's as though the moon has a kind of electric haze at dawn. The composition of the regolith contributes to this effect. The grains have sharp edges and an irregular shape which helps them retain charges. Unlike Earth's dust, which gets rounded by erosion, lunar dust keeps its angular shape. This increases the surface area and makes the electrical interactions more complex. The result is a material that is unstable on a microscopic level. Understanding this phenomenon is crucial for designing future equipment. Rovers, habitats, and scientific instruments will need to withstand environments where charged particles move unpredictably. Since lunar soil is extremely dry, there's no natural way for the charges to neutralize. On Earth, moisture helps discharge electrically unstable surfaces, but on the moon, the absence of liquid water creates an environment where charge buildup is constant. Even a simple movement by an astronaut can trigger the suspension of nearby dust particles. This invisible effect affects everything around it. The idea that soil can react to sunlight without combustion might seem strange at first, but in space, the principles of electricity behave differently. A simple beam of radiation can start a chain reaction among particles, and since regolith covers almost the entire moon, this effect can spread across vast areas. Studying lunar regolith is not only important for lunar exploration, but it also helps us anticipate challenges for other planetary missions. Airless bodies like asteroids or moons of Mars might exhibit similar phenomena. Understanding the behaviour of regolith on the moon gives us a glimpse into the challenges we may face on other planets. Each particle that levitates tells part of a story that is still being uncovered. The moon preserves the sun's lost history on its surface. Unlike Earth, the moon has no atmosphere or weather to change its outer layers, which means its surface has stayed almost the same for billions of years. Every dust particle and exposed rock holds a direct record of radiation and particles from space, including solar winds made up of protons and electrons from the sun. When these particles strike the lunar regolith, they penetrate only a few micrometers into the soil. There, they become trapped between the grains, forming layers that act as a physical record of solar activity. Without any erosion, these layers remain intact over time. This enables scientists to study the sun's history continuously, gaining access to particles that were released billions of years ago. The moon's soil preserves this record with an accuracy that Earth cannot offer. Samples brought back by the Apollo missions revealed the presence of atoms directly implanted by the solar wind. Elements like helium-3, neon, and argon were found in different amounts depending on the depth of the sample. These variations show how the intensity and composition of the solar wind changed over time. The differences observed between layers point to solar cycles that occurred long before life appeared on Earth. Some of these elements are extremely rare on Earth because the atmosphere blocks them from reaching the ground. On the Moon, without this barrier, they accumulate directly. This makes the regolith one of the only accessible records of ancient solar events. Isotopic analysis of these elements provides data on the Sun's temperature and magnetic activity throughout different periods. Each sample functions as a compact time capsule. Beyond solar winds, the Moon also records particles from more extreme events like coronal mass ejections. These high-energy particles can travel deeper into the soil and alter its structure. In some samples, traces of massive solar events have been found, which left no noticeable records on Earth, because Earth's atmosphere absorbed their impact, while the regolith preserved them perfectly. The distribution of these particles also offers clues about the Sun's axial tilt in the past. Variations in the angle of solar wind impact affect where and how intensely elements accumulate. With data gathered from different regions of the Moon, it is possible to reconstruct parts of the Sun's behavior over time. The differences between samples from the near side and the far side of the Moon also show how the Moon's orbital position influences this accumulation. In addition to solar particles, the Moon also records cosmic rays from outside the solar system. These ultra-high energy particles collide with the regolith and cause nuclear reactions on a microscopic scale. The byproducts of these reactions remain stored in the soil, allowing scientists to study cosmic radiation over billions of years. This type of data is hard to obtain anywhere else in the solar system. These reactions create specific isotopes that can be dated with great precision. This allows scientists to link certain periods of lunar history to distinct levels of cosmic radiation. During times of lower solar activity, for example, more cosmic rays reach the surface. Correlating this data helps understand the solar system's energy balance over different periods. In this way, the Moon acts as a natural measuring tool. By combining data on depth, composition, and location, scientists can build a detailed timeline of the Moon's interaction with space. This includes solar cycles, cosmic storms, and phases of heightened galactic activity. No other celestial body near Earth offers such a continuous record. The Moon's geological stability makes it the perfect foundation for this kind of analysis. Some of the preserved particles also carry chemical signatures linked to the Sun's formation. Specific isotopes of neon and argon can reveal details of the solar wind during its earliest stages. This extends the usefulness of the regolith beyond recent solar cycles. In certain cases, scientists can trace these particles back to remnants of the original nebula that formed our solar system. These traces have remained locked between lunar dust grains for billions of years. Material taken from different depths of the regolith also helps scientists measure the rate of dust deposition over time. This reveals how often the Moon was hit by micrometeorites, which in turn affects the soil's exposure to radiation. This allows scientists to calculate how long certain layers stayed exposed before they were buried. Each level of soil tells part of that story. The fact that the Moon has no atmosphere, magnetic field, or significant tectonic activity ensures that all these records remain almost entirely undisturbed. This turns the surface of the Moon into a long-term physical database. The Moon had volcanic activity more recently than they previously thought. For a long time, the Moon was believed to be geologically inactive. The large, dark plains known as the Maria were thought to be the remnants of ancient eruptions that happened billions of years ago. These regions cover about 17% of the lunar surface and were believed to mark the end of a long geological era. However, recent observations have challenged that view, suggesting that the Moon may have remained active for much longer. Detailed images captured by the Lunar Reconnaissance Orbiter, LRO, revealed formations that were not on earlier maps. These small volcanic deposits are scattered in areas where no recent activity was expected. They are smaller, more irregular and show little erosion. Estimates based on crater counts suggest these formations are less than 100 million years old, which is extremely recent on a geological timescale. Some of these deposits show signs of explosive eruptions. Fragments of glassy material formed from gas-rich lava have been detected in these areas. This indicates that the Moon's interior still had enough heat and pressure to sustain volcanism even after billions of years of cooling. These fragments differ from older lava flows, which were denser and more uniform. The contrast suggests that there were different phases of volcanic activity over time. These recently discovered formations are scattered across various parts of the Moon. One area, called ENA, features hills and depressions with little erosion. The surface texture resembles solidified foam with smooth edges and sharp contours. This is unusual for formations exposed for millions of years without an atmosphere. The low number of craters in this area strengthens the idea that these features are geologically young. In addition to visual observations, spectral data confirms that the composition of these areas is different. The minerals present indicate rapid cooling and incomplete crystallization, which are typical signs of recent volcanic flows. The coloration of these regions is slightly lighter than that of the ancient Maria, helping to identify them with sensors. The reason why the Moon continued to produce eruptions much later than expected is still debated. One possibility is that isolated magma pockets were trapped in the lunar mantle, protected from complete cooling. These pockets could have been activated by internal stresses or even asteroid impacts. Another theory is that radioactive elements within the Moon generated enough heat to keep parts of the interior partially molten. Gravimetry studies show that the Moon's interior is not completely uniform. Some areas have lower density, which may correspond to zones of partially melted material. This uneven distribution helps explain why some areas of the Moon stayed active for longer. It also suggests that lunar volcanic activity didn't stop abruptly, but instead became more localized over time. The identified volcanic formations do not have the extensive lava channels seen in the ancient Maria. Instead, they are smaller, more concentrated, and have a variety of shapes. This points to a different kind of volcanic activity, less intense but still significant. Some features show signs of partial collapse, as though the ground had sunk after magma chambers emptied. These circular structures resemble small calderas with broken edges and sunken floors. They support the idea that internal activity continued when these features were formed. Even without tectonics like Earth's, the Moon shows signs of small-scale internal movement. The discovery of these regions has changed how scientists view the Moon's thermal evolution. It was once believed that the Moon had cooled completely over 1 billion years ago, but now it's known that parts of its interior retained heat for much longer. This new discovery opens up possibilities for understanding how radioactive elements and heat were distributed in small planetary bodies. Even though the Moon is cold in most parts, there are still zones of underground activity. These findings have also led to a re-evaluation of age maps of the lunar surface. Some areas that were once thought to be ancient have been reclassified based on new evidence. This affects our understanding of impact rates and the overall timeline of the solar system. With more high-resolution images, new features are continually being found, and the idea of a completely inactive Moon is no longer valid. The Moon's gravitational field is so irregular that probes have lost control in certain areas. In some regions of the lunar surface, the gravitational field doesn't follow the expected patterns. These anomalies, known as mascons, occur where there is a higher concentration of mass beneath the surface. They alter the local gravity and directly affect any object in orbit. Mascons were first discovered during early lunar missions when probes began losing altitude unexpectedly. Some of these orbiters, both American and Soviet, experienced partial failures due to these gravitational distortions. They were designed using approximate gravitational models that did not consider such variations. When passing over mascon areas, their paths underwent subtle but cumulative shifts. In a short period, this caused altitude loss and instability. This pattern continued until the anomalies were accurately mapped. Mascons are typically found in ancient impact basins. In these regions, the violent collision caused dense materials from the Moon's interior to rise. As they gathered beneath the crust, they created zones with stronger gravity. The most famous of these regions is the Imbrium Basin, which contains a large mass concentration just below its surface. Other basins, such as Serenitatis and Crescem, show similar behavior. These anomalies also affect satellites in low lunar orbit. Missions like NASA's Lunar Prospector and Grail were crucial in understanding the distribution of mascons. They helped create highly accurate gravitational maps. These maps show that the Moon's gravity changes over distances of tens of kilometers, which is unusual for bodies with low geological activity. These variations occur even in regions that appear visually uniform. The influence of mascons is strong enough to alter a probe's orbital period. Small accumulated changes affect the time it takes to complete a lunar orbit. Without constant adjustments, the orbit quickly deteriorates. For this reason, modern missions must calculate their paths to avoid these areas or adjust them in real time. Navigation around the Moon relies heavily on a detailed understanding of these anomalies. In addition to complicating missions, mascons reveal important details about the Moon's internal structure. For example, the depth of these mass concentrations helps estimate the thickness of the crust and the density of the mantle. This provides insights into the satellite's thermal evolution and the behavior of materials following ancient impacts. The irregular distribution of mascons suggests that these processes were not uniform. These anomalies are also useful for testing physical models that apply to other celestial bodies. Planets like Mars and Mercury have similar, though less intense, structures. Studying lunar mascons allows scientists to test impact simulations and gravitational behavior in environments with low mass. In some cases, local gravity is so strong that it even affects the path of light reflected by sensors. This impacts altimetry measurements and must be compensated for during terrain analysis. Without these corrections, the apparent relief of the surface can appear deeper or higher than it really is. The precision of lunar images is directly tied to the gravitational model being used. During the Grail mission, 2 twin satellites were placed into orbit to measure these variations with unprecedented accuracy. They recorded small distance changes between each other caused by gravitational anomalies beneath the surface. This method allowed the mapping of smaller mascons that were invisible to previous techniques. The data revealed that some regions of the Moon's crust are thinner than previously believed. These findings also showed how lunar gravity affects areas near recent craters. Some of these zones are beginning to show signs of small mascons forming, possibly due to impacts and localized mass redistribution. This suggests that such structures might still be forming, even on a body thought to be geologically inactive. The Moon's gravity is far from uniform and is marked by surprising contrasts. The impact of these findings has altered our basic understanding of the Moon's structure as a solid body. The old idea that the satellite is made of simple static layers has been replaced by a more dynamic model. Even without visible volcanism or tectonics, internal mass redistribution continues to play a significant role in orbital behavior and crustal evolution. The Moon might have formed from a collision with a planet the size of Mars. The current theory about the Moon's origin involves one of the most violent events in Earth's history. According to the giant impact hypothesis, our planet collided with a celestial body roughly the size of Mars about 4.5 billion years ago. This body has been named Theia. The collision is thought to have sent massive amounts of material into space, forming a debris disk around Earth. The Moon is believed to have formed from this disk. Simulations of this process suggest that the ejected material concentrated into a stable orbit just above Earth. Within a few hundred years, these fragments began to clump together under gravity. The heat generated by the collision kept this material partly molten. The early Moon would have formed as a sphere of magma that cooled slowly over time. This explains the absence of certain volatile elements in its interior. One of the strongest pieces of evidence for this hypothesis is the isotopic similarity between rocks from Earth and the Moon. Elements like oxygen, silicon, and titanium show nearly identical chemical signatures. This suggests that both bodies originated from the same source material. Other moons in the solar system, which formed through gravitational capture or direct accretion, do not share these characteristics. The Moon's composition is much closer to Earth's crust than any other body. Additionally, the Moon's current orbit supports this theory. Its orbital plane, distance from Earth, and rotational speed match what is expected from material that was ejected. The tilt of its axis and its gravitational locking, which causes it to always show the same face, may have been established soon after the formation. These factors support the idea that the Moon is partially the result of a massive rearrangement after a catastrophic impact. Other models have attempted to explain the moon's formation through different processes, such as capturing a wandering body or simultaneous accretion, but these theories fail to explain the chemical similarities and the observed orbital stability. The giant impact theory remains the most robust, though there is still debate over the mass, composition, and trajectory of Theia. The impact likely occurred at a relatively shallow angle, which helped disperse material widely. Recent studies have tried to estimate what happened to Theia's remnants. Some of the material may have been incorporated into Earth's mantle, while other parts formed the Moon. Some models suggest that Theia's metallic core may now be deep within Earth, mixed with its own core. Others propose that leftover fragments might still be orbiting the Sun as Trojan asteroids. The exact origin of Theia is still unclear. The heat from the initial impact may have kept the Moon's interior molten for millions of years. During this period, denser minerals sank while lighter materials rose to the surface. This process, called differentiation, created the mineral-rich crust that covers the Moon's highlands. This crust is still visible today, especially on the Moon's far side. The newly formed Moon was much closer to Earth than it is now. It is estimated that in its early stages, it completed an orbit in less than 10 hours. This closeness caused extreme tides on Earth, which directly affected the planet's climate and rotation. Over time, the Moon gradually receded, a process that continues today at a rate of about 3.8 cm per year. This retreat is measured using laser ranging from reflectors placed by the Apollo missions. Even after billions of years, the original impact still influences the relationship between Earth and the Moon. The tilt of Earth's axis, the stability of its climate, and even the length of the days are all tied to the Moon's presence. The Moon acts as a natural stabilizer, reducing extreme fluctuations on Earth. And all of this began with a single planet-scale event. The impact may have also vaporized much of Earth's early atmosphere. The energy released was sufficient to melt entire surfaces and create magma oceans. Thermal models show that Earth took hundreds of thousands of years to cool after the collision. This cooling period coincided with the formation of the first solid crustal structures. The giant impact hypothesis not only explains the Moon's formation, but also links its origin to Earth's early history. The physical and chemical connection between the two bodies is a direct result of this event. Every lunar rock carries clues from this shared past, preserved in an environment without erosion or tectonics. The more we study this scenario, the more it reinforces the idea that the Moon and Earth have a common origin shaped by the chaos of the solar system's beginnings. The Moon was once covered by a global ocean of magma. Shortly after its formation, the Moon looked very different from how it does today. Due to the intense heat from the impact that created it, its surface remained molten for a long time. This molten state created a global ocean of magma that covered nearly the entire surface of the satellite. This phase is estimated to have lasted for tens of millions of years. During this time, the Moon was a glowing sphere of liquid rock. As the magma cooled, lighter minerals began to solidify and rise to the surface. This led to the formation of the Moon's initial crust, mostly composed of anorthosite. This white, calcium-rich rock is found in abundance in the lunar highlands. Meanwhile, the denser minerals sank, forming the mantle. This separation process, known as magmatic differentiation, still defines the Moon's internal structure today. Geological records from this time are preserved in samples returned by the Apollo missions. Anorthositic rocks, dated at over 4.4 billion years old, confirm the existence of this early magma ocean. The chemical makeup of these rocks is consistent with large-scale magma crystallization. Furthermore, their widespread presence suggests that the process occurred across the entire Moon, not just in specific areas. During the cooling of the ocean, distinct layers formed within the lunar crust. The lower layers crystallized first, containing minerals like olivine and pyroxene. The upper layers, richer in plagioclase, accumulated above them. This vertical layering can still be observed in deep impact basins, where impacts have exposed interior layers. These records help scientists reconstruct the Moon's cooling timeline. In regions where the crust was thinner, residual magma found paths to the surface, forming large lunar maria from basaltic lava flows. These maria are darker and denser than the highlands, and their composition reflects a deeper origin. The shift from a global magma ocean to localized eruptions marks a significant change in the Moon's internal activity. Orbital spectrometer studies confirm these compositional differences. The older, lighter-colored areas are rich in aluminum and calcium, while the darker maria contain higher levels of iron and magnesium. This distribution follows the expected pattern for a body that underwent differentiation from a global magma source. The Moon's surface is essentially a frozen map of its own solidification process. The magma ocean model also explains the absence of volatile elements on the Moon. At such high temperatures, elements like hydrogen, helium and water were rapidly lost to space, leaving the Moon dry with no significant atmosphere. The remaining minerals are almost entirely refractory, meaning they are resistant to extreme heat. This chemical trait is found in nearly all lunar samples. The solidification of the ocean also affected the Moon's thermal structure. As new layers formed, they trapped heat inside, creating insulation that kept the mantle warm for hundreds of millions of years. This residual heat powered the volcanism that later formed the Maria. Even today, some interior regions still exhibit higher temperatures. The formation of the crust from molten magma also created internal stresses. As the Moon cooled, its volume decreased slightly, causing compression in the outer crust. This compression created geological faults and fractures, some of which can still be observed with telescopes. In recent missions, some of these faults have been mapped in high resolution, revealing structures that stretch hundreds of kilometers. The existence of a global magma ocean makes the Moon one of the best examples of planetary differentiation that can be observed. Unlike Earth, whose surface has been shaped by erosion, tectonics, and climate, the Moon preserves its original crust. Every deep crater on the Moon acts as a window into the layers formed in its earliest moments. The record of this ancient ocean remains visible today, frozen in the Moon's topography. The Moon also has permanently shadowed regions that are colder than Pluto. Near the Moon's south pole, there are deep craters whose rims block sunlight from entering. These areas, known as permanently shadowed regions, never receive direct sunlight. Due to their extreme tilt and the terrain's geometry, they have remained in complete darkness for billions of years. As a result, they reach some of the lowest temperatures ever recorded in the solar system. Measurements from NASA's Lunar Reconnaissance Orbiter have shown that some of these regions reach temperatures as low as 248 degrees Celsius, colder than Pluto, which is more than 5 billion kilometers away from the Sun. The lack of light and atmosphere prevents any warming, so even during the lunar day, these craters remain thermally isolated. Only the exposed edges see slight temperature increases. These conditions create an ideal environment for preserving volatile materials. Any water molecules that reach these regions are likely to freeze instantly. Without processes like sublimation, the ice remains stable for billions of years. This makes these craters natural ice reservoirs, shielded from the thermal variations that affect the rest of the Moon. The ice may be mixed with regolith, or found in pure layers in the coldest areas. The origin of this ice is linked to the slow deposition of molecules from comets, meteorites, and even the solar wind. Over time, small amounts have accumulated in the shadowed regions. Spectroscopic studies have confirmed the presence of hydroxyls and traces of water in these areas. In some locations, there's evidence of solid ice preserved just beneath the surface, found in craters like Shackleton, Hayworth, and Cabas. Permanently shadowed regions also have distinct optical properties. The soil there is darker and less reflective than the rest of the lunar surface. This is because the regolith in these areas doesn't undergo the same space weathering effects. Without solar radiation, the particles retain more primitive physical characteristics, which also affects how heat is absorbed and emitted. In addition to large craters, small depressions and recesses can create microenvironments of permanent shadow. These smaller sites haven't been fully mapped yet, but some already show signs of ice or volatile compounds. The ice distribution is more fragmented than previously thought, varying with cavity depth, slope, and orientation. This challenges earlier models that predicted continuous ice deposits. Temperature measurements in these regions are made with orbital thermal sensing instruments, which detect infrared radiation emitted by the ground even in these cold conditions. These readings require high precision, as heat emission is extremely low. The data collected has been compared with thermal propagation models, confirming that solar heat does not penetrate these craters at any point during the lunar year. Despite being on the Moon's surface, these areas behave like near interplanetary environments. The absence of heat, light, and atmosphere creates a stable thermal vacuum. This makes them valuable for testing space instruments and studying physical processes at extreme temperatures. The behavior of materials and radiation in such harsh conditions is still being researched. The ice found in these regions shows no signs of recent movement or migration. It is bound to the regolith and distributed irregularly, with concentrations depending on the local morphology. In many cases, the ice is located less than 10 cm beneath the surface. Even in these thin layers, the presence of water molecules confirms that these deposits have persisted for billions of years. Permanently shadowed regions remain one of the most mysterious parts of the lunar surface. Even with detailed orbital mapping, their full depth and composition are still not entirely understood. Accessing these craters requires highly precise landings and vehicles capable of functioning in extreme temperatures. Some future missions are already being designed to explore these regions, hoping to uncover what else might be preserved in these pockets of perpetual darkness. There are also peaks on the Moon that receive nearly constant sunlight. While most of the Moon alternates between long periods of day and night, certain high regions near the poles receive almost continuous sunlight. These areas are known as peaks of eternal light. This occurs due to the Moon's small axial tilt of only about 1.5 degrees, which allows certain high points to remain in sunlight, even when the sun is low on the horizon. These peaks are usually located on the rims of deep craters, particularly near the lunar North Pole. The surrounding topography creates a favourable geometry. While depressions remain in permanent shadow, the highest points stay visible to the sun. This condition doesn't guarantee constant sunlight, but does provide extended periods of illumination with only brief interruptions during the lunar year. These regions receive the highest continuous light exposure across the entire Moon. Observations from the Clementine and LRO missions have identified at least 4 areas that receive over 80% sunlight exposure throughout the year. One promising peak is near the Piri crater, where sunlight is continuous for days or even weeks at a time. During the lunar summer, solar exposure reaches nearly 100%. This creates rare thermal stability on the Moon's surface, where temperatures typically fluctuate dramatically between day and night. The constant sunlight in these peaks also affects local temperatures, keeping them much more moderate than those in shadowed areas, which can drop to 170 degrees at night. The surface heats up gradually, and the heat is not released suddenly. This helps reduce thermal stress on materials and allows electronics and solar panels to function for longer periods. This feature makes the peaks of eternal light extremely appealing for future scientific missions. The consistent availability of solar energy simplifies the design of probes, landers, and robotic stations. Additionally, their proximity to permanently shadowed areas, where ice can be found, offers a strategic advantage: access to frozen water and the energy required to use it. As a result, many lunar exploration projects prioritize these regions in their planning. Even though these peaks receive abundant sunlight, they still face the harsh conditions of space. Solar and cosmic radiation persist, and the soil remains dry and abrasive. However, the thermal stability and extended periods of sunlight provide distinct advantages. The sun's low angle relative to the horizon casts long, consistent shadows, which helps in high-precision topographical mapping. Simulated lighting studies indicate that even when the sun doesn't directly shine on the peaks, reflected light from surrounding slopes continues to illuminate the area. This further shortens the duration of darkness. 3D topographic models have been used to pinpoint the locations with the greatest sunlight exposure, guiding the selection of future landing sites. Another important factor is that the sun's position changes very little near the lunar poles throughout the lunar cycles. This predictability aids in automated operations. While most of the Moon experiences a night lasting 14 Earth days, these peaks receive enough continuous light to maintain uninterrupted activity for weeks. This is vital for missions that rely on constant power generation. The exact extent and composition of the soil at these peaks remain unknown. They haven't been directly explored by any mission, and most of the data comes from orbital sensors. However, high-resolution images suggest that the surfaces are rocky and relatively stable. The lack of deep craters indicates they may be among the Moon's oldest and least disturbed regions. The contrast between these peaks and the surrounding permanently shadowed craters creates an extreme difference in environmental conditions. In just a few kilometers, you can move from one of the coldest places in the solar system to one of the most sunlit. This spatial contrast, combined with stable lighting, makes the peaks of eternal light one of the most unique and strategically valuable areas on the Moon's surface. The Moon experiences quakes caused by extreme thermal expansion. Contrary to common belief, the Moon is not entirely still. It experiences seismic activity, known as moonquakes, which occur for various reasons. One of the most interesting causes is the thermal expansion of the crust. During the transition between lunar night and day, surface temperatures can fluctuate by more than 270 degrees. This temperature difference causes rocks heated by the sun to expand suddenly. The resulting stress causes the surface layers to crack, shift, or compress, creating small tremors that spread locally and can last for several minutes. Unlike earthquakes, which are sudden, these lunar events start gradually with a slow build-up of intensity. Seismometers deployed during the Apollo missions detected these vibrations numerous times. Thermal quakes typically occur at lunar sunrise when the sun begins to shine after 2 weeks of darkness. The rock, which has been contracted and frozen for days, heats up rapidly and expands unevenly. This leads to cracking, fractures, and internal movements. In some instances, there are records of tremors strong enough to displace objects and affect equipment on the surface. Apart from thermal expansion, other types of moonquakes have been identified, including those caused by gravitational tidal forces from Earth, internal contraction of the lunar core, and even meteorite impacts. However, thermal quakes are the most predictable as they follow the rhythm of the daylight cycle. These quakes especially affect regions near the equator where temperature variation is most pronounced. The energy involved in these events is lower than that of large earthquakes on Earth, but they last significantly longer. Some lunar quakes have lasted more than 10 minutes. This is because the Moon's internal structure is dry, rigid, and lacks damping, allowing seismic waves to travel with little energy loss, making even small vibrations last for extended periods. The seismometers placed by Apollo 12, 14, 15, and 16 recorded over 12,000 seismic events over an 8-year period. Some of these events were directly linked to thermal surface variations. These data helped map the Moon's most active regions and provided valuable insights into its internal structure. Based on these findings, scientists now know that the Moon has a partially fractured mantle and a smaller core than previously thought. The tremors also help explain certain surface features. Some cracks and geological faults may have been aggravated by repeated cycles of expansion and contraction. These patterns create rectangular or stepped structures that cut through the regolith. On sloped terrain, thermal quakes can trigger small landslides, gradually redistributing dust and rocks. Even without Earth-like tectonic activity, the Moon shows internal dynamics on various scales. The mere presence of thermal variation is enough to keep its crust in a constant state of adjustment. This shows that seismic activity can emerge in unexpected ways, even on bodies that seem geologically inactive. The data collected from seismometers remains one of the primary sources of information about the Moon's interior. These phenomena are being considered when planning future permanent installations on the Moon. Structures exposed to the surface will need to withstand cycles of expansion and contraction, as well as prolonged vibrations. This includes habitats, power systems, and scientific robots. Resistance to thermal quakes will be crucial for the long-term durability of lunar operations. Radiation on the Moon can cause genetic mutations in humans. Unlike Earth, the Moon has no thick atmosphere or magnetic field to protect it from space radiation. This means its surface is constantly bombarded by high-energy particles from the Sun and distant cosmic sources. These particles include solar protons, galactic cosmic rays, and intense ultraviolet radiation, all capable of penetrating living tissue and damaging cellular structures. During the Apollo missions, astronauts were exposed to this hostile environment for relatively short periods. Even so, they required reinforced suits and shielding for the modules to minimize the effects. Studies based on collected data now estimate that the average radiation dose on the moon's surface is about 200 times higher than what a person experiences on Earth. With prolonged exposure, this dose can exceed safety limits set for human activity. The energetic particles striking the moon interact directly with the skin, eyes, and internal organs. They cause ionization in cells, breaking molecules and damaging DNA. This process disrupts cell division and can result in genetic mutations. While some of these mutations are naturally repaired by the body, others accumulate over time, increasing the risk of degenerative diseases, including cancer. Laboratory experiments with human cells exposed to simulated cosmic radiation have confirmed the occurrence of double-strand breaks in DNA, one of the most difficult types of damage to repair. These particles can also disrupt cellular organelles and trigger long-lasting inflammatory responses. The effects are not immediate, but they worsen with prolonged exposure and individual genetic vulnerability. There is virtually no natural shelter from radiation on the moon, except for caves or underground lava tubes. Even during the lunar night, cosmic radiation continues to penetrate without obstruction. This makes the risk constant and independent of the solar cycle. During coronal mass ejections, when the sun releases large amounts of energetic particles, the radiation intensity can increase dozens of times within hours. Prolonged exposure can lead to neurological degeneration, cognitive impairment, immune system damage, and accelerated aging of cells. These effects are most severe in tissues with high cell turnover rates, such as the intestines, skin, and bone marrow. Animal simulations have also shown impacts on fertility and behavioral changes, further complicating the challenge of maintaining safe human life on the moon's surface. Electronic devices are also impacted by radiation. Energetic particles can cause malfunctions in circuits and interfere with sensor readings. For this reason, both humans and autonomous systems require specific protection. Aluminum, for example, is commonly used as a protective shield, but it is less effective against certain types of cosmic rays. Materials like polyethylene and hydrogen-rich compounds have shown to be more effective at blocking high-energy particles. Even lunar dust contributes to the radiation exposure risk. Electrically charged particles stick to the skin, clothing, and equipment, making decontamination challenging. Some of these particles are small enough to enter the respiratory system and act as abrasives. While these particles do not emit radiation themselves, they can act as reactive surfaces that increase the damage caused by external radiation. Lunar radiation remains one of the greatest obstacles for sustaining human presence on the moon. Each new data set from probes and simulations helps improve risk models and guide the development of better protection strategies for future missions. Even short-term exposure requires careful planning and strict protocols to ensure the safety of the crew. In 2018, researchers announced the discovery of a massive metallic structure buried beneath the moon's crust. This colossal mass was located beneath the South Pole Aitken Basin, one of the moon's largest and oldest impact craters. The anomaly was detected through gravitational measurements from NASA's Grail mission, which revealed an unusually dense region beneath the lunar surface. The mass is estimated to weigh around 2.4 to 4 billion tons and spans over 300 kilometers in width, lying approximately 300 kilometers deep. This region of the moon had already been recognized for its geological significance. The basin itself measures more than 2,000 kilometers in diameter and is located on the far side of the moon. The impact that created it was so powerful that it penetrated the crust and reached the lower mantle. The discovery of this dense mass at the center of the structure raises important questions about its origin and role in lunar evolution. One leading theory is that it consists of leftover metal from the asteroid that caused the impact. Data shows that this mass is rich in elements like iron and nickel, which are typically found in metallic cores of differentiated celestial bodies. However, the distribution and density of the mass suggests that it is not concentrated in a single spot, but spread out over a broad area, as though it had been partially melted or mixed with the surrounding mantle. This makes it challenging to determine the exact origin and behavior of the structure over time. Another theory proposes that the metallic material accumulated after the impact, sinking into the crust through a process of gravitational migration. This occurs when denser materials separate from lighter ones and settle into deeper layers. The pressure from the impact may have forced this molten material downward, where it has remained ever since. Computer models show that the presence of this metallic mass significantly alters the local gravitational field. This affects not only the region's topography, but also the path of spacecraft flying over or landing in the area. The anomaly causes subtle changes in the velocity of orbiting probes, which were essential for accurately detecting the mass. These gravitational deviations allow scientists to map the Moon's internal structure without drilling. The exact origin of the metallic mass remains a topic of debate. Some scientists propose that it could be the remnant of a differentiated core from a protoplanet that collided with the Moon during the early solar system. If this is the case, the structure could be a preserved fragment of a primitive planetary body, frozen within the Moon for billions of years, making this region one of the oldest and most intriguing parts of the lunar crust. The discovery has also prompted scientists to re-examine theories about the formation of the Moon's far side. Evidence suggests that this hemisphere evolved differently from the near side, with a thicker crust and distinct impact patterns. The presence of the metallic mass may have influenced this process by affecting the distribution of internal heat and the formation of secondary basins. Because of this, the Atkin Basin has become a top priority target for future lunar missions. Images of the region show a rugged landscape with internal mountains and concentric rings. The basin's geological complexity is highlighted by the presence of this anomaly. Though sensors cannot directly penetrate to the core of the metallic mass, indirect measurements confirm its existence with high confidence. It is one of the largest high-density structures ever detected outside Earth, and studying it could provide new insights into how rocky bodies evolve in space. The Moon emits an invisible tail of radioactive particles, much like a comet. Despite appearing inactive, the Moon interacts intensely with the solar wind. When high-energy particles from the solar wind strike the surface, they release neutral atoms and ions from the regolith. Among these elements is sodium, which has fluorescent properties and behaves differently in the vacuum of space. These sodium atoms form a faint cloud around the Moon known as the exosphere. During the new Moon phase, when the Moon is positioned between Earth and the Sun, this sodium cloud is pushed by the solar wind in the opposite direction of the Sun. The result is an elongated structure, a true sodium tail, that extends for more than 100,000 kilometers. This tail is invisible to the naked eye, but can be detected using instruments that capture the light emitted by sodium when it is excited by solar radiation. The specific emission occurs at a wavelength known as the D line in the visible spectrum, which is used in astronomical spectroscopy. Ground-based observatories have successfully mapped the tail during certain periods of the lunar month. The phenomenon becomes more noticeable during periods of heightened solar activity, such as coronal mass ejections. During these events, the tail becomes denser and brighter, making it easier to detect. The intensity of the tail varies depending on the Moon's surface topography and composition. Areas rich in sodium, such as certain ancient Maya plains, contribute more to the sodium cloud. The inclination of the Moon's orbit also affects the angle of the solar wind, which, in turn, influences the tail's orientation and density throughout the year, creating dynamic patterns similar to those observed in comets. Experiments conducted by spacecraft like Leia have helped measure the particle fluxes and confirmed that sodium is a major component of the lunar exosphere. Other elements detected in smaller amounts include potassium, calcium, and magnesium. Although present in very low concentrations, these atoms help researchers understand how the Moon's surface interacts with the surrounding space environment. Unlike comet tails, which are created by the sublimation of ice, the Moon's tail is formed by the direct physical and chemical release of atoms from rocks under intense radiation. Continuous bombardment breaks atomic bonds in the regolith and releases atoms into space. This process is not explosive but continuous and diffuse, creating a persistent emission of particles that has been happening for billions of years. The sodium tail is scientifically important because it is one of the few ways to study the lunar exosphere remotely. Since it extends beyond the Moon's orbit, it can be observed from Earth, allowing researchers to monitor changes without relying solely on space probes. Variations in its intensity serve as indirect indicators of local solar activity. During specific alignments of the Sun, Moon, and Earth, the tail projects toward us. During these moments, observatories with high-sensitivity spectrometers can detect the faint glow produced by reflected sunlight. This phenomenon has been observed on multiple occasions, confirming the tail's existence and extent with high precision. The structure behaves like a beam with a preferred direction. The presence of this tail shows that the Moon is not a completely passive body. Even without an atmosphere or magnetic field, it continuously responds to external conditions. The regolith acts as an active surface, releasing particles when bombarded, a process known as sputtering. This same mechanism occurs on other airless bodies, such as Mercury and various moons and asteroids. The tail poses no threat to Earth or spacecraft due to its extreme rarity. With a density of only a few hundred atoms per cubic centimetre, well below the threshold detectable by conventional instruments. Nonetheless, the distribution pattern of particles provides valuable information about the physics of airless surfaces in deep space and helps refine models of space weathering. Currently, the lunar tail is monitored alongside other observations of the exosphere. Projects like the Lunar Sodium Project aim to improve our understanding of how these flows change in response to meteor showers and variations in solar activity. These features led to theories that some rocks may have originated in microgravity conditions. One of the most studied samples, called the Genesis rock, shows signs that it formed within a suspended debris cloud. In these environments, mineral grains do not settle due to gravity. Instead, they slowly fuse while floating. This allows crystals to grow in multiple directions, giving the rock a spongy or porous texture. The absence of vertical sedimentation is a clear indicator that the rock formed in weightless or near-weightless conditions. The most likely environments for this type of rock formation are impact plumes or ejecta regions shortly after a violent collision. When an asteroid strikes the lunar surface, it creates a temporary cloud of molten particles that can remain suspended for several minutes. During this brief period, local gravity is effectively cancelled out by the particles' acceleration. Rocks formed in this environment solidify with unique textures. Laboratory analysis shows that some of these rocks contain tiny gas bubbles trapped inside as the material cools under low pressure. These bubbles are small and randomly distributed, unlike those in typical lava-formed rocks. This suggests that the cooling occurred in a rarefied environment without a solid surface shaping the rock. The spherical shapes of the bubbles are typical of solidification in free-float conditions. Another striking feature is the presence of glass clusters with varied compositions. These fragments mix with larger crystals, creating chaotic patterns that are unlikely to form in normal lava flows. The samples suggest that diverse materials partially melted and fused while floating in mid-air, followed by rapid and disordered solidification. This supports the theory of formation in suspension. Microgravity conditions also preserve delicate structures. Under normal gravity, fragile fragments tend to collapse or merge before they can solidify. However, in the absence of weight, such structures can remain stable for a longer time, allowing uncommon geometries to form. Some lunar rocks show these properties at a microscopic level. Computer simulations have modelled the behaviour of molten debris after major impacts. Results show that particles can remain suspended for tens of seconds, long enough for crystallization to begin. Electrostatic forces also influence particle movement, encouraging clusters to form without relying on gravity. These factors together create rock textures that are rarely seen on Earth. Rocks formed in microgravity are particularly interesting to planetary science. They are similar to structures found in certain meteorites and on asteroid surfaces. This similarity helps researchers make connections between different celestial bodies and gain insights into the processes that occur during cosmic collisions. The Moon, lacking an atmosphere, preserves these records with remarkable accuracy. Not all unusually shaped rocks are formed in microgravity. Some may have been altered by later impacts or intense radiation. However, the combination of physical and chemical characteristics in certain samples consistently points to their formation while suspended. The difficulty in replicating such conditions in the lab only increases the scientific value of these discoveries. The variety of lunar rocks shows that the Moon's surface has captured a broad spectrum of geological events. From flowing lava to molten particles suspended in air, the Moon's history is written in microscopic detail across its rocks. Radiation on the Moon can cause genetic mutations in humans. Unlike Earth, the Moon has no thick atmosphere or magnetic field to protect it from space radiation. As a result, its surface is continuously bombarded by high-energy particles from both the Sun and distant cosmic sources. These radiation sources include protons, electrons, and heavy atomic nuclei. When they hit the lunar surface, they can penetrate several centimeters into solid materials. Any living organism present would be vulnerable to significant cellular damage. During the Apollo missions, astronauts were only exposed for short periods and were shielded by limited protective measures. However, modern data indicates that the radiation dose on the Moon's surface can be more than 300 times greater than Earth's background radiation. Prolonged exposure to this radiation can directly affect human DNA, causing double-strand breaks, changes to nitrogenous bases, and failures in cellular repair processes. These effects are cumulative and difficult to reverse. Experiments conducted outside the International Space Station have helped estimate biological damage in exposed tissues. Even in low Earth orbit, where Earth's magnetic field provides partial shielding, cells show detectable mutations. On the Moon, without such protection, the exposure would be much more intense. Radiation can cause replication errors, silent mutations, or cell death through apoptosis. Over time, this increases the risk of cancer and degenerative diseases. Another concern is the radiation from unpredictable solar events. Solar storms can release bursts of energetic particles that can penetrate conventional shielding. Future missions will need to predict and avoid such events, as direct exposure could lead to acute effects like nausea, internal burns, and immune suppression. Subsurface shelters or water-based shielding are considered viable protection strategies. Studies of radiation-resistant organisms, such as certain bacteria and lichens, have shown that radiation can alter reproductive cycles and cause random mutations. These changes can affect proteins, membranes, and self-repair mechanisms. While some mutations are neutral, many disrupt cellular function. The lunar environment not only exposes organisms to radiation, but also impairs their ability to recover from damage. Research also indicates that radiation interacts with lunar soil, generating secondary particles. When high-energy protons strike the regolith, they trigger nuclear reactions that release neutrons and gamma rays. These byproducts can penetrate physical shielding and reach nearby biological material, broadening the risk beyond direct radiation. This highlights the need for careful assessment of landing site environments. Computer models estimate that on a 6-month mission to the Moon, an astronaut could receive a dose of radiation exceeding the safety limits set by space agencies. This would require limiting time spent on the surface or using advanced shielding. Materials such as polyethylene and hydrogen-rich compounds have shown promise in blocking cosmic radiation, but are bulky and complex to transport. Human DNA is especially vulnerable to ionizing radiation-induced double-strand breaks, which are difficult to repair without causing errors, potentially resulting in chromosomal translocations or complete gene deletions. Even cells that survive these alterations may display undesirable phenotypic changes. In multicellular organisms, these errors accumulate over time, impairing vital biological functions. There is also concern about hereditary effects. If germ cells are exposed, mutations could be passed on to offspring, leading to genetic anomalies. Animal studies have demonstrated this risk in high radiation and microgravity environments. While direct human data is limited, comparative biology strongly suggests the need for extreme caution. Reproduction in the lunar environment would require robust protective barriers. In addition to DNA damage, cosmic radiation can affect neural structures and cognitive functions. Rodent studies have shown memory deficits, behavioral changes, and brain inflammation after prolonged exposure. These effects are especially concerning for long-term missions. The nervous system is highly sensitive to radiation-induced free radicals, which disrupt neurotransmitter and synaptic networks. Radiation also affects electronics, causing failures in medical equipment, sensors, and communication systems. High-energy particles may pass through circuits, inducing readout errors or complete malfunctions. This directly impacts crew safety, requiring redundancy in critical systems. Biological sensors and radiation detectors will be essential for providing real-time alerts to sudden environmental changes. based on current data, any extended human presence on the Moon will depend on carefully designed strategies to limit radiation exposure. With temperatures dropping below 170 degrees Celsius and no direct sunlight for billions of years, these areas serve as natural cryogenic traps. Gases and volatile compounds deposited in these regions would remain almost unchanged over geological timescales. Missions like Alcross and the Lunar Reconnaissance Orbiter have already detected hydrogen, frozen water, and possible traces of noble gases such as argon and xenon in polar craters. These elements are especially valuable for study because they are chemically stable and retain isotopic signatures. By comparing these signatures with those of Earth's present atmosphere and those expected from early Earth, scientists can identify potential correlations and non-lunar origins. Some samples collected by the Apollo missions and analysed using mass spectrometers have shown noble gas isotopes in ratios different from the typical lunar ones. These variations suggest the possibility that material from Earth was directly captured by the Moon. This theory is supported by the hypothesis that during the early Earth-Moon system phase, Earth's magnetic field temporarily extended to the Moon's orbit. This could have guided charged particles, especially light ions, to the Moon's surface. Additionally, the Moon may have had its own magnetic field in the past. Paleomagnetic records found in lunar rocks show that for hundreds of millions of years, it maintained an internal dynamo capable of generating a temporary magnetic field. This field may have helped protect the surface and retain light particles, particularly in permanently shadowed regions where no sublimation or erosion could occur. Currently, shadow craters are among the highest priorities for scientific exploration. Drilling into deep regolith, untouched by solar radiation and secondary impacts, could reveal layers with intact traces of Earth's primitive atmosphere. Such a discovery would have far-reaching implications for understanding Earth's origin, atmospheric evolution, and even the chemistry necessary for life's origin. However, the technical difficulty of such sampling is immense. Samples must be kept below 200 degrees throughout the extraction and transport process to prevent the sublimation of fragile gases. Proposals have been made to use probes equipped with cryogenic drills and thermal containment systems. NASA and ISSE missions are already considering these technologies to explore craters like Shoemaker, Faustini, and Haworth. If confirmed, this primitive atmospheric record would be unique in the solar system. Earth's tectonic and climatic dynamics have erased almost all direct evidence of its early history. On the other hand, the Moon has preserved its surface layers nearly intact, serving as a geological archive of Earth's history. The idea that Earth's past may be stored, frozen, and preserved in the darkness of lunar craters turns these regions into natural laboratories for astrobiology and geoscience. The Moon has magnetic swirls that form patterns visible from space. On its surface, there are mysterious formations that stand out because of their bright and winding appearance, known as lunar swirls. Unlike craters and mountains, these patterns do not have a geological origin. They are contrasting brightness patterns across the regolith, the Moon's soil, and can be seen from space by orbital probes. The most well-known example is Rhina Gamma, a spiral-shaped structure located on the Moon's near side, about 70 kilometers across. The primary explanation for these swirls involves localized magnetic fields. Although the Moon lacks a global magnetic field like Earth's, some regions of its crust retain remnant magnetization, fragments of the magnetic field that existed in the past. These magnetic fields act as partial shields against the solar wind, a continuous stream of charged particles from the Sun. When the solar wind strikes unprotected regolith, it triggers space weathering, which darkens the minerals over time. However, in regions with swirls, the magnetic field deflects some of these particles, shielding the soil and preserving its original lighter colour. This contrast with surrounding areas creates visible patterns, like streaks of light on a darkened surface. The shape of the swirls is determined by the geometry of the local magnetic fields, not by surface features. In some regions, the patterns spread out as broad bands, while in others they form curves, spirals, and bifurcations. The morphology of the swirls corresponds to the contours of the magnetic anomalies identified by missions such as Lunar Prospector and Artemis, indicating a direct connection between magnetism and surface appearance. The origin of these localized magnetic fields remains under debate. A widely accepted theory suggests that they were formed during impacts from comets or metallic asteroids. These impacts, due to intense heat and the presence of external magnetic fields, magnetize local minerals. Another theory proposes that areas rich in ferromagnetic minerals retained ancient magnetic fields during the Moon's cooling phase, before its internal dynamo collapsed. The swirls are not exclusive to the near side of the Moon. Some of these formations have been found on the far side as well, suggesting that this phenomenon can occur wherever magnetization is preserved. Recent missions, equipped with high-sensitivity imaging spectrometers, continue to map new patterns, analyzing subtle differences in surface reflectance. The composition of the regolith also affects the visual intensity of the swirls. Areas rich in iron and titanium oxides are more susceptible to space weathering, which makes the protective effect of the magnetic fields more noticeable. This results in high-contrast visual zones that highlight the swirls in orbital imagery. Beyond their scientific and aesthetic value, lunar swirls may have practical applications. Since these magnetic fields deflect part of the solar radiation and reduce surface degradation, researchers are exploring whether these regions could serve as natural shields to protect equipment, sensors, or long-term structures in future lunar missions. Magnetic swirls represent a unique phenomenon that merges geophysics, solar interaction, and mineral properties. They are clear examples of how invisible forces, like magnetism, can create visible patterns on seemingly inactive celestial bodies. They also reinforce the idea that, although the Moon lacks tectonics or an atmosphere, it still possesses a surprisingly rich and complex dynamic. Some lunar craters are colder than Pluto, with temperatures below 240 degrees Celsius. At the Moon's poles, there are craters that never receive direct sunlight. These deep depressions, known as permanently shadowed craters, maintain temperatures so low that they surpass the coldest recorded on Pluto, a dwarf planet nearly 30 times farther from the Sun. Measurements from the Lunar Reconnaissance Orbiter, LRO, have identified temperatures as low as 248 degrees in these regions, just 25 degrees above absolute zero. This extreme condition is caused by two main factors: the Moon's small axial tilt of just 1.5 degrees and the rugged topography of the polar regions. Since the Sun never rises very high on the lunar horizon, its rays cannot reach the bottoms of craters near the poles. As a result, these areas remain in constant shadow for billions of years, receiving no direct thermal energy. Moreover, the Moon lacks a significant atmosphere, which prevents heat redistribution. Therefore, shadowed regions do not receive warmth from nearby sunlit areas as happens on Earth through conduction or convection. Instead, heat escapes directly into space, making the interiors of these craters some of the coldest environments in the entire solar system among rocky bodies. These extremely low temperatures make the shadowed craters particularly interesting for scientific and space exploration purposes. They act as cold traps capable of preserving water ice and other volatiles like carbon dioxide, ammonia, and even organic compounds. Many of these materials were deposited by comets or released through internal processes and have remained frozen for geological ages. Spectroscopic instruments on the LRO and LCROSS missions have already detected signs of water ice in the regolith of these craters. Some of these deposits lie on the surface, while others are mixed deeper into the soil. The presence of ice could be vital for future human missions, providing drinking water, oxygen, and hydrogen-based fuel. However, exploring these regions presents an extreme technical challenge. Equipment must operate in temperatures below 240 degrees C, requiring advanced insulation, heating, and material resilience solutions. Additionally, conventional solar power systems are ineffective due to the lack of light, making alternative energy sources like nuclear batteries or thermoelectric generators necessary. These craters also help scientists understand the Moon's thermal climate and serve as models for studying similar environments on other celestial bodies like Mercury, Ceres, and some moons of Jupiter and Saturn. Understanding how heat is retained or lost in airless areas is crucial for planning stable space habitats and long-term scientific operations. Hermit Crater, located near the Moon's North Pole, is one of the coldest places ever measured, with temperatures estimated to be below 240 degrees Celsius. Along with other craters like Shoemaker, Haworth, and Cabas, it is a prime target for upcoming missions by NASA, ISRO, and other space agencies. These sites are promising candidates for resource extraction and deep geological studies. Beyond their resource value, the lack of direct solar radiation in these regions means minimal chemical degradation, allowing ancient materials to be preserved with exceptional fidelity. These craters might hold records of the solar system's history, including chemical compounds, minerals, and even solar wind particles that were trapped billions of years ago. The thermal differences in these regions are extreme. The sunlit crater rim, which can reach temperatures of 120 degrees C, contrasts sharply with the shadowy interior at 240 degrees, creating a gradient that can exceed 360 degrees within just a few kilometers. This makes these craters excellent testing grounds for engineering materials, thermal simulations, and equipment trials designed for hostile environments. In summary, the Moon's ultra-cold craters are like natural frozen vaults, preserving valuable resources and offering clues about the history of Earth, the Moon, and the solar system itself. Missions aimed at penetrating these shadowed zones could access materials that have been virtually untouched since the formation of the planets, potentially revolutionizing our understanding of water's origins, prebiotic chemistry, and planetary evolution. Lunar dust is so dry that it can absorb moisture from human skin. Lunar regolith, the Moon's surface soil, is one of the most inhospitable materials ever studied. Formed through the continuous fragmentation of rocks over billions of years by micrometeorites and solar radiation, it consists of extremely fine, angular, and dry particles. Unlike Earth, the Moon has no water or air, so the regolith has undergone no erosion. This makes the material highly chemically reactive and capable of absorbing moisture. During the Apollo missions, astronauts reported that lunar dust clung easily to clothing and skin, causing itching, eye irritation, and respiratory discomfort. Some particles even penetrated spacesuits and the command modules, where they were inhaled in small amounts. Upon contact with skin, astronauts noticed an immediate sensation of dryness, as if the moisture was being drawn out. Subsequent laboratory studies confirmed that lunar regolith behaves hygroscopically. It rapidly absorbs water even in low humidity. This absorption is not due to internal water, but because of the chemical structure of the grains, which have unsaturated bonds and highly active surfaces that readily bind with H2O molecules. Moreover, regolith contains a variety of minerals such as olivine, pyroxene, and amorphous glass formed by impacts, all of which react quickly with moisture. The absence of atmosphere and weathering softening processes gives the dust an irregular, sharp shape, unlike Earth's dust, which is rounded due to erosion. This increases friction and adhesion to surfaces, including human skin, particularly in oily or sweaty areas. Lunar dust also carries a high electrostatic charge, especially after exposure to solar radiation. This makes it stick to clothing, equipment, and plastic surfaces. During Apollo 17, astronauts observed that it was nearly impossible to keep the module clean. Dust spread throughout the interior, worsening respiratory and maintenance issues. Even more concerning is that regolith can damage the respiratory system. Inhaled particles cause inflammatory reactions similar to those caused by silica or asbestos on Earth. They are small enough to penetrate deeply into the lungs and may contain compounds that react with oxygen, creating potentially toxic substances. Prolonged exposure can lead to serious pulmonary issues, especially on long missions. The dust's abrasive properties also extend to equipment, spacesuits, and mechanical joints. Being fine and sharp, it infiltrates the smallest crevices, damaging moving parts. The dust harms seals, wears down fabrics, and interferes with solar panels and sensors. Its removal is difficult. Traditional brushing methods are ineffective, and the vacuum of space complicates conventional cleaning techniques. To tackle this, scientists are experimenting with self-cleaning materials, protective films, and technologies based on electrostatic pulses or magnetic fields. Some of these solutions are inspired by materials developed for harsh industrial environments but need to be adapted for the Moon's vacuum, radiation, and extreme temperatures. Dust management is considered a critical issue for lunar habitability. Despite being hazardous, lunar dust also presents scientific and technological opportunities. It is rich in oxygen, which can be extracted through chemical reduction processes for breathing or fuel. Regolith can also be compacted into bricks or structures, reducing the need to transport materials from Earth. However, handling it requires careful containment systems to avoid health risks. Finally, detailed analysis of regolith provides valuable insights into the history of the lunar surface, revealing the frequency and intensity of impacts over time. Grain size distribution, mineral composition, and the presence of glassy particles indicate the processes that shape the moon's crust. Each particle serves as a microgeological record of billions of years of events. In short, lunar dust is more than just a technical nuisance. It is a challenge to health, engineering, and exploration. But it is also a valuable source of information and resources. Its ability to absorb moisture from human skin highlights the stark difference between the moon's environment and Earth's, and why lunar colonization will require innovative and thoughtful solutions. The moon also has an invisible sodium halo that glows under certain light conditions. Although the moon appears to be completely devoid of atmosphere, it has a tenuous and nearly imperceptible exosphere composed of isolated atoms that rarely collide with one another. One of the most intriguing components of this exosphere is sodium, which forms a diffuse halo around the moon, extending tens or even hundreds of thousands of kilometers into space. This halo is invisible to the naked eye, but it can be detected with sensitive spectroscopic instruments. The sodium in the lunar exosphere is released from the regolith, the moon's extremely dry and fragmented surface soil. Ejection occurs through several processes such as micrometeorite impacts that vaporize parts of the surface, ultraviolet radiation, and bombardment by solar wind particles that break chemical bonds and expel atoms. Once released, these atoms are temporarily retained by the moon's gravity, orbiting for a time before escaping into space or returning to the surface. The presence of this halo was confirmed through spectroscopic observations made from Earth, especially during lunar eclipses. During these events, Earth's shadow blocks direct sunlight, allowing instruments to detect the faint glow of sodium at a specific wavelength, the D line, around 589 nanometers. The same wavelength emitted by sodium vapor lamps. This spectral signature is strong enough to reveal the presence of sodium even in extremely low concentrations. This sodium halo is not symmetrical. It extends in the direction opposite the Sun, forming a structure similar to a comet's tail. This is because solar radiation pressure pushes the atoms away from the light source, creating a structure that can extend more than 100,000 kilometers, enveloping the entire moon in an invisible asymmetrical haze. The halo's intensity fluctuates with solar activity. During periods of increased radiation and particle emissions, such as coronal mass ejections, the sodium flux in the exosphere increases. This allows scientists to monitor the interaction between the moon and the space environment and understand how bodies without a dense atmosphere respond to the solar wind. In addition to sodium, other elements like potassium, argon, helium, and traces of hydrogen have been detected in smaller quantities. However, sodium stands out for its characteristic glow, making it easier to detect with telescopes using specific filters. Missions such as the Lunar Atmosphere and Dust Environment Explorer have confirmed these observations from lunar orbit. The sodium halo challenges the previous belief that the moon is a completely inert body without an atmosphere. Although extremely rarefied, the moon's exosphere is dynamic and responds to solar activity. The composition and variation of the halo help map the moon's surface chemistry, revealing regional differences in sodium distribution. Moreover, the cycle of atom ejection and return to the surface maintains a continuous renewal of the regolith's outer layer. Each exposed particle can be chemically or physically altered by these processes, even affecting reflectance and spectroscopic measurements made by probes. From a practical standpoint, the sodium halo influences the planning of future missions. Scientific instruments sensitive to atmospheric or spectroscopic composition need to account for the presence of this layer. In regions near the sodium tail's ejection line, measurements may be slightly altered by this atomic haze. This phenomenon is not unique to the moon. Planets like Mercury and some of Jupiter's moons exhibit even more intense sodium halos, allowing scientists to compare similar behaviors in bodies with little or no atmosphere. Analyzing these structures helps to understand the physics of the interaction between planetary surfaces and interplanetary space. In summary, the Moon's sodium halo is a subtle yet significant feature that demonstrates how even an apparently inert body maintains a constant interaction with its cosmic environment. It is further proof that the Moon, far from being a dead world, is an active laboratory for planetary and space physics. The Moon's core is still partially molten. The internal structure of the Moon is made up of several layers, including the crust, mantle, and core. For a long time it was believed that the Moon's interior had completely solidified. However, recent seismic and gravitational data suggest that the Moon's core still retains a partially liquid portion. This discovery has altered the way we understand the thermal evolution of the Moon's interior. The first clues came from seismometers placed during the Apollo missions, which detected unusual seismic wave reflections. These data were later reanalyzed with modern techniques, suggesting the presence of an interface between solid and liquid material in the core. Current models now indicate that the Moon's core has a solid inner core surrounded by a partially molten outer layer. This structure mirrors that of Earth's internal setup, but on a much smaller scale. It is estimated that the Moon's core has a radius of about 330 km, with the liquid portion occupying roughly 30% of that. This molten layer is believed to consist of an iron alloy with small amounts of sulfur and nickel. The sulfur lowers the melting point of iron, allowing it to remain liquid at lower temperatures, making the core more complex than originally thought. The existence of this liquid layer also helps explain certain orbital and gravitational behaviors of the Moon. Anomalies in its moment of inertia and axial wobble, known as libration, are consistent with the presence of a partially liquid core. These observations, combined with satellite data, have allowed scientists to create three-dimensional models of the Moon's interior, indirectly confirming the partial liquidity. Additionally, the Moon's gravitational field shows subtle variations indicating internal movement. These oscillations, although small, suggest there's activity beneath the surface. The molten layer could be exerting torque on the solid parts of the core, subtly affecting the Moon's rotation, a change that is only detectable with high-precision instruments. The origin of the Moon's internal heat remains a topic of ongoing research. Some of the remaining heat is residual from the Moon's formation, when intense collisions and gravitational differentiation heated its interior. Another factor is the presence of radioactive elements such as uranium, thorium, and potassium, which may still be present in the deep mantle. These elements release heat as they decay, helping to maintain part of the core in a liquid state. Despite the partially molten core, the Moon does not have an active global magnetic field like Earth's. However, there is evidence that it once did. Magnetized lunar rocks suggest that billions of years ago, the Moon had an internal dynamo capable of generating a strong magnetic field. As the Moon's interior cooled, the dynamo gradually faded and eventually disappeared. Understanding the Moon's core is vital for studying the geological evolution of natural satellites. The presence of liquid layers can extend internal convection processes, potentially sustaining some tectonic or thermal activity. While the Moon's activity is limited, it may have influenced ancient events like volcanism and the solid tides that still cause small moonquakes. Thermal models suggest that the core's liquid portion could solidify completely over the next few billion years, depending on heat loss rates and the exact composition of the internal metallic alloy. Ongoing studies using orbital missions and computer simulations continue to refine predictions about this process. The knowledge of the Moon's internal structure also informs the exploration of other rocky bodies. Future seismic instruments, more sensitive than those used during the Apollo missions, could confirm the exact depth and composition of the core. Proposals are in place to send probes capable of detecting P and S waves generated by lunar impacts. These data would assist in building a more detailed model of the Moon's interior and help resolve remaining questions about its core dynamics. Comparing the Moon's core with those of other celestial bodies like Mercury or Jupiter's moons offers further context for understanding lunar observations. Each satellite has a different internal configuration shaped by its thermal and compositional history. By studying these patterns, scientists can identify both common trends and unique characteristics in planetary core formation. The confirmation that the Moon's core is partially molten represents one of the most significant advances in lunar science in recent years. This discovery challenged the old theories about the complete cessation of the moon's internal activity. Studies conducted in various parts of the world indicate that lunar cycles may have an effect on human sleep quality. Controlled experiments have shown that during the full moon, sleep latency tends to increase and deep sleep duration decreases. This pattern was observed even in environments with no exposure to natural light, ruling out moonlight as the sole factor. The consistency of these results suggests an influence not yet fully understood. A study published in Current Biology monitored brainwaves, hormone secretion, and sleep behavior in a laboratory setting. During the full moon, volunteers took about 5 minutes longer to fall asleep, slept 20 minutes less, and experienced less deep sleep. There was also a drop in melatonin levels, the hormone associated with sleep onset. The data showed a statistically significant correlation with the lunar cycle. Other studies with tribes without access to electric light also found sleep variations aligned with the moon's phases. Even without artificial lighting, their sleep patterns changed in sync with the lunar cycle. This suggests that the phenomenon may have a deep biological basis, possibly tied to ancestral circadian rhythms. The natural synchronization with the nighttime environment may have been preserved through evolution. Researchers have explored the possibility that the human biological clock might be sensitive to lunar cycles. These cycles last about 29.5 days, close to the average duration of the menstrual cycle and other physiological fluctuations. Some theories propose that this synchronization could be embedded in ancient hormonal mechanisms. However, there is still no consensus on whether specific receptors or processes detect the moon's phase. The moon's gravitational influence on the human body is often considered too weak to have a noticeable effect. Nonetheless, there are speculations that the periodic repetition of gravitational cycles, combined with the brain's sensitivity to natural rhythms, could play a role. This hypothesis is similar to how certain animals use lunar cycles for reproduction, migration, or feeding. However, there is still no direct physiological evidence in humans. Individual variability also complicates the identification of a universal pattern. Some people seem to experience no change in sleep during the lunar cycle, while others report recurring disturbances. Susceptibility may depend on genetic, environmental, or behavioral factors. Studies have also looked into how the full moon might influence hormone levels of the melatonin. Some studies have shown fluctuations in cortisol levels, which affect alertness and show a correlation with the lunar cycle. However, these results are inconsistent across different populations and data collection methods. The challenge lies in distinguishing real effects from statistical variations or external influences. Another area of investigation is the unconscious perception of moonlight. Even with eyes closed, receptors in the skin and retina are sensitive to ambient light. On full moon nights, this indirect light might influence hormone production. While this effect might not be consciously detected, it could still act on regulatory sleep mechanisms. This hypothesis is currently being tested with ultra-sensitive light sensors. Researchers are also studying a potential connection between lunar sleep patterns and dream activity. Anecdotal evidence suggests more vivid dreams occur more frequently during full moons. Electroencephalography (EEG) is being used to see if these subjective experiences correlate with specific sleep stages, like REM sleep. However, the data is still scarce and inconclusive. Chronobiology, the study of biological rhythms, has begun to incorporate the lunar cycle into its models. Traditionally, this field has focused on the 24-hour circadian rhythm, but lunar studies have shown that monthly cycles may also have an effect. The goal is to integrate these lunar patterns into more complex models of hormonal regulation, metabolism, and behavioral neuroscience. Advancements in wearable sensors like smartwatches and sleep monitors now enable large-scale data collection. With these devices, scientists can track sleep patterns in thousands of people over multiple lunar cycles. This could reveal subtle trends that were previously undetectable, further supporting or refuting current hypotheses about lunar influence. Lunar mascons also create unexplained local gravity variations. During the first lunar missions, engineers noticed unusual behavior in spacecraft. Orbital trajectories experienced small repeated disturbances in certain regions of the moon. These deviations indicated local variations in the gravitational field that were inconsistent with expected uniformity. Over time, these anomalies were named mascons, short for mass concentrations. Mascons are areas with higher subsurface density, which slightly increases local gravity. They are mostly linked to large impact basins filled with denser material. The Imbrium Basin, one of the largest lunar craters visible from Earth, is a prime example. Gravity in this region is significantly stronger than in surrounding areas, which directly affects the movement of probes and satellites in low orbit. The presence of mascons was confirmed by missions like the Lunar Prospector and more recently NASA's Grail spacecraft. These missions precisely mapped the Moon's gravitational field, showing detailed patterns of anomalies. The data indicated that mascons are not only found on the surface but also buried deep beneath several kilometers of crust. Although the mass buildup is invisible to the naked eye, it affects the surrounding space. The exact cause of mascons is still debated. One theory suggests that after asteroid impacts, partially molten mantle material rose to fill the crater. This material, being denser than the surrounding crust, created a mass anomaly. Another theory proposes that dense materials were already present before the impact and were exposed or concentrated during the event. Both explanations imply a complex and varied lunar interior. These gravitational anomalies not only affect spacecraft but also influence the paths of lunar missions. During the Apollo missions, careful adjustments had to be made to account for mascons. Without these adjustments, the spacecraft could have followed unstable trajectories when approaching certain areas. Knowing about these anomalies beforehand was crucial for mission safety. Even with updated models, some mascons are still not fully understood. Some areas display complex gravitational patterns that do not fit existing simulations. This suggests that the Moon's interior might have irregular layers with materials of unknown origin. The interior structure seems to be more diverse than we thought. In addition to affecting gravity, mascons also alter the shape of the Moon's crust. The pressure from the concentrated mass can slowly distort the surface, creating subtle bumps. High-resolution satellite images have identified some of these deformations around ancient basins. This interaction between the mass and the crust is an ongoing study in lunar geophysics. The presence of mascons makes it hard to predict orbits around the Moon. Satellites in low orbit must be constantly adjusted to maintain their position. This factor is considered when designing new missions, which often choose higher or elliptical orbits to avoid the effects of mascons. Planning long-term missions requires mapping these regions carefully. Mascons also raise questions about how the Moon's crust was formed. If these mass concentrations formed soon after the impacts, it suggests that the crust was still partly molten or soft at the time. This helps scientists estimate the Moon's thermal history and understand its geological evolution. These clues are important for understanding how planets cool and solidify over time. Comparisons with other moons in the solar system show that mascons also exist on bodies like Mars and Mercury. However, the intensity and number of these anomalies vary, reflecting each planet's unique thermal and geological history. Studying mascons on the Moon provides an accessible model to study similar phenomena on other distant planets, making the Moon an excellent laboratory for gravitational studies. Data from the Grail mission enabled the creation of 3D maps of the Moon's gravity with exceptional detail. These models are used for orbital simulations, impact studies, and crustal analysis. By combining this information with topographic data, scientists can estimate the depth and density of mascons. This continues to enhance our understanding of the Moon's internal structure. Ongoing investigations of the Moon's gravitational variations are refining earlier models. Future missions are expected to use more sensitive sensors and AI algorithms to detect smaller anomalies. The presence of mascons, though invisible to the naked eye, continues to shape the Moon's gravitational field in surprising ways. In unexpected ways, the Moon holds fossilized records of meteorites erased from Earth's history. During the first 700 million years of Earth's existence, the planet was constantly bombarded by meteorites. This period, known as the Late Heavy Bombardment, left deep marks on Earth's evolution. However, Earth's geological activity erased almost all those records. The planet's crust was constantly reshaped by tectonic plates, erosion, and volcanism. On the other hand, the Moon, without an atmosphere or tectonic activity, has preserved those scars. Lunar craters serve as nearly perfect archives of ancient events in the solar system. Every impact recorded there may correspond to similar events on Earth. Studying these marks gives scientists an indirect view of Earth's lost history. The distribution of craters and the minerals in their rims help estimate how frequently impacts occurred. This allows scientists to recreate parts of Earth's early landscape. Meteorite fragments that struck the Moon have remained intact for billions of years. They weren't altered by water, wind, or internal heat, making them valuable for understanding the composition of celestial bodies from the early solar system. Some rocks collected during the Apollo missions contain material from extraterrestrial sources dating back over 4 billion years. Such traces would be impossible to find on Earth. Comparing lunar craters with those on asteroids helps scientists identify common impact patterns. These patterns reveal information about the dynamics of objects that once orbited near Earth. It's also possible to link types of lunar minerals with meteorite families found today. This creates a connection between modern samples and ancient processes. In this way, the Moon acts as a parallel geological library. Computer models suggest that many meteorites that collided with Earth would have left similar marks on the Moon. Since the two bodies are close in size, relevant impacts likely affected both. Therefore, the distribution of lunar craters can point to specific events that changed Earth's history. The absence of these records on Earth makes the Moon even more important for this study. The Artemis missions and others planned for the future aim to study these cratered regions more closely. The goal is to collect soil samples that contain primitive meteorites. New techniques, such as dating and spectroscopy, will allow detailed analysis of these samples. Scientists expect to find chemical signatures of materials that have disappeared from Earth, such as metal-rich compounds, exotic silicates, and volatile minerals. Lunar soil also preserves evidence of solar and cosmic radiation, helping scientists date specific periods of bombardment. The stratigraphy of surface layers helps scientists piece together the history of impacts. Each layer represents a chronological record of successive collisions. This type of analysis provides insight into the asteroid belt's evolution and the orbital instability of giant planets. Another key factor is the location of the samples. The oldest impact basins are more likely to contain meteorites from the early solar system. Samples from these regions may reveal materials formed before the Moon even existed, offering clues about the formation of the protoplanetary disk and the conditions of interplanetary space in its early phase. Some scientists are also looking for signs of organic compounds in these ancient remnants. Although the Moon doesn't support life, carbon-rich meteorites could have left behind organic residues, suggesting the presence of such compounds in other early celestial bodies. Future studies may test this possibility in more detail. The absence of erosion and atmosphere means that crater surfaces have preserved impact features, from radial marks to compression rings. These details help scientists understand how the energy from impacts is spread, and also help estimate the size and speed of objects that struck the surface. All of this makes the Moon a unique resource for studying planetary origins, not just for itself, but for Earth's early history as well. The Atkin Basin, located on the far side of the Moon, is one of the largest impact structures in the solar system. Measuring 2,500 kilometers in diameter and 8 kilometers deep, it far exceeds any known terrestrial depression. For comparison, the Grand Canyon is only about 1.6 kilometers deep, while the Atkin Basin reaches nearly 5 times that depth. The basin was formed by a massive impact about 4 billion years ago, which excavated deep layers of the lunar crust. The impact was so intense that it may have reached the mantle, revealing materials rarely accessible on the Moon. This makes the region strategically important for geological research. The basin's extreme depth was confirmed by altimetry instruments from missions like Japan's Kaguya and NASA's Lunar Reconnaissance Orbiter. These missions created detailed 3D topographic models of the site, showing steep reliefs, long valleys, and circular mountain ranges. The region is one of the most complex on the Moon's surface. The floor of the basin contains high concentrations of minerals rich in iron and titanium, indicating the presence of differentiated rocks from deeper layers. Minerals like pyroxenes and olivines typically found in the mantle, have also been detected. This material offers a unique chance to study the Moon's interior without the need for drilling. At the centre of the basin lies a large plateau called Montes Lineis. This elevated area may have formed as a result of the crust rebounding after the impact, which also happens in large craters on Earth and Mars. However, on the Moon, the lack of erosion has preserved this structure for billions of years. Because the basin is located on the Moon's far side, it cannot be seen directly from Earth. Therefore, its study relies on orbital images and remote sensing data. For many years, this limited our complete understanding of the region. Today, robotic missions are filling in the missing pieces. In 2018, China's Chang'e 4 spacecraft became the first to land inside the basin. The site was chosen because of its geological interest. The goal was to study the soil, measure its composition, and look for signs of material from the Moon's mantle. Early data has shown notable differences from other regions, with the soil being more complex and varied. The Atkin Basin is also being considered for future lunar bases. Its location near the poles provides more stable temperatures and possible access to frozen water in shadowed craters. Additionally, its mineral wealth makes it a potentially valuable site for resource use in place. These factors increase interest in future missions. The structure of the basin also affects the local gravity, creating one of the largest gravity anomalies on the Moon. This suggests a significant accumulation of mass beneath the surface. Studying these anomalies helps estimate the depth of the crust and the density of materials inside. The data is combined with seismic models to give a clearer picture of the Moon's interior. Comparing the Atkin Basin with similar structures on Mars and Mercury highlights striking differences. The Moon's lack of atmosphere has allowed for excellent preservation of features, making it easier to analyse the impact processes. The basin has become a benchmark for comparison with other planetary formations. The enormous size of the Atkin Basin continues to challenge our models of impacts and the Moon's crust development. Its size and depth suggest a massive energy event. Understanding how the crust responded to this impact can provide clues about the strength and makeup of the Moon's interior. This region remains a key focus of modern lunar research. The Moon reflects Earth's radio signals like a cosmic mirror. While the Moon does not generate its own radio waves, it can reflect signals from Earth. Powerful radio waves, especially those used in radar and military communication, can bounce off the lunar surface and return to Earth. This effect is known as Earth-Moon-Earth (EME) communication. The Moon acts as a passive reflector, sending signals over vast distances. The reflections follow predictable paths based on the Moon's position. During World War II, scientists first noticed strange radar echoes and later realized they were coming from the Moon. This discovery became a tool for long-range radio communication experiments. In the 1950s, the US military conducted tests known as Project Diana, where they bounced signals off the Moon and received them on another continent, marking the start of passive lunar radar science. The strength of the reflected signals depends on factors like the angle of incidence, frequency, and the surface roughness. High-frequency waves tend to scatter, while lower-frequency signals reflect more clearly. Despite the Moon's rocky, irregular surface, it behaves like a diffuse reflector, meaning some signals scatter while a large portion returns in a focused direction. This has been used to measure distances with extreme precision. Occasionally, radio telescopes on Earth detect echoes from terrestrial broadcasts reflected off the Moon. These signals include radar pulses, television broadcasts, and even FM radio waves. The reflected signals are extremely weak, trillions of times weaker than the original signals, but sensitive instruments can detect them. This passive reflection allows researchers to study both the lunar surface and Earth's emissions. The strength and delay of the returning signals provide clues about the Moon's surface texture and density. In radio astronomy, these measurements help build detailed models of the Moon's surface structure. Even subtle features like buried rock layers or lava tubes can affect how signals return. Repeated measurements show changes over time, such as dust movement or surface degradation. The Moon's ability to reflect radio waves has raised concerns about interference, especially for lunar missions. Space agencies must account for these reflections when planning communications. Reflected signals could interfere with sensitive equipment or be misinterpreted as signals from extraterrestrial sources. To ensure accuracy, filtering and calibration are essential for interpreting data. One proposed use of the moon's reflective properties is passive radar imaging of Earth. In theory, signals sent from Earth and reflected off the moon could create shadowy images of terrestrial features. While this technique isn't practical yet, it has been explored in simulations and classified military projects. The moon serves as a reliable reflector in this scenario, and the Earth-Moon-Earth effect has been adapted for amateur radio experiments. Enthusiasts with powerful antennas send signals to the moon and wait for the echo. This is considered a highly challenging achievement in the hobby, allowing communication between distant stations that would otherwise be unreachable. The delay in the echo adds a unique experience to the exchange. In addition to communication, the moon's reflection has been used to detect Earth's electromagnetic leakage into space. Scientists have measured the amount of radio noise Earth emits into space by analysing its bounce back. This has implications for the search for extraterrestrial intelligence, as it helps define how detectable Earth might be to distant observers. The moon offers a unique reference point for these calculations. Reflecting radar signals also helps test and calibrate planetary radar systems. The Goldstone Deep Space Complex and other facilities have used the moon to refine their instruments. The consistency of the reflections helps reduce noise in space-based measurements, and this method remains a standard calibration technique in radar astronomy. Not all lunar regions reflect radio signals equally. Smooth plains like the Sea of Tranquility give more consistent echoes than the rugged highlands. By comparing these differences, scientists can classify surface types without needing to land. Variations in reflectivity also help identify areas of interest for future missions. The moon's role in Earth-based transmissions has revealed its unexpected usefulness as a scientific tool. Although silent and inert, it contributes to long-range experiments just by existing in the right place. As a cosmic mirror, the moon continues to help us study the invisible patterns of our electromagnetic environment. During a total lunar eclipse, the moon passes through Earth's shadow but doesn't completely disappear. Instead, it glows with a reddish hue. This happens because sunlight passing through Earth's atmosphere is scattered and bent, redirecting some of it toward the moon. The light reaching the lunar surface carries information about the gases and particles in Earth's atmosphere. In this way, the moon acts as a giant projection screen. This phenomenon is called atmospheric limb scattering. As sunlight skims across Earth's edge, it passes through a thick layer of air, which filters and bends the light. The light that survives this journey is heavily influenced by dust, ozone, aerosols, and other atmospheric components. The resulting glow is a mix of all the filtering effects. Each eclipse provides a unique snapshot of Earth's atmosphere at that moment. Scientists use high-resolution spectroscopy during eclipses to analyze the light that illuminates the moon. By breaking it into wavelengths, they can detect gases like nitrogen dioxide, ozone, and even volcanic ash. These spectral signatures offer real-time indicators of air quality and climate dynamics, turning each eclipse into an observational platform for Earth science. Changes in the color and brightness of eclipses over decades track long-term atmospheric trends. For example, after volcanic eruptions, eclipses often appear darker due to increased aerosol concentrations in the stratosphere. By comparing historical eclipse data, researchers can reconstruct timelines of atmospheric disruption. The moon effectively archives these events through its light. Lunar eclipse spectroscopy has been refined using modern instruments on ground-based observatories. During an eclipse, telescopes gather light data at precise intervals, and sophisticated software helps separate the features of the atmosphere from the lunar reflectance. The result is a highly accurate profile of Earth's atmosphere, covering a wide range of the planet's surface. This method has even been proposed for studying exoplanets by observing how starlight passes through an exoplanet's atmosphere. The Earth-Moon eclipse system provides a model for studying distant planets. Our atmosphere is like a test for new techniques before we try them outside the solar system. Every eclipse gives us a chance to check the global conditions at the same time from different places. Telescopes on various continents collect data, helping us create a worldwide picture. These coordinated efforts allow scientists to check their measurements and spot any unusual patterns. This teamwork has improved how we track changes in Earth's atmosphere in real time. Lunar eclipses can even help us find gases that are usually hard to detect. Sometimes pollutants like nitrogen dioxide or sulfur dioxide are easier to spot during an eclipse. These observations help support the data from satellites and ground-based measurements, especially in places that are hard to reach. The eclipse's global nature improves our atmospheric coverage. The moon's surface, with its predictable reflectance, makes it easier to understand the incoming light. Since the moon's surface is mostly stable, any changes in light are likely from Earth's atmosphere. This stability makes the moon perfect for long-term atmospheric monitoring. It also helps improve the reliability of comparisons made between different eclipses. The length and strength of an eclipse affect how well scientists can collect data. Longer eclipses provide more time to observe and allow for better tracking of atmospheric changes over time. They also make it easier to measure atmospheric layers that depend on altitude. The depth of the shadow during an eclipse changes how light behaves and penetrates. Eclipses are particularly useful for studying ozone layers and dust in the stratosphere, which leave unique traces in the light spectrum. By focusing on these traces, researchers can learn about the health of Earth's protective layers and spot any signs of damage early. This helps with climate studies and global environmental monitoring. Even though lunar eclipses are visually stunning, they play an important role in atmospheric science. Each eclipse becomes a natural experiment that gives scientists worldwide insights without needing satellites. As long as the moon keeps orbiting and Earth's shadow crosses it, these celestial events will continue to reveal the hidden dynamics of our atmosphere. The moon also contains helium-3, a rare isotope that could be used in nuclear fusion. Helium-3 is lighter than regular helium, as it has 2 protons and 1 neutron. On Earth, helium-3 is rare and hard to extract, but on the moon it is found in the upper layers of lunar soil. This is because the solar wind has deposited helium-3 on the moon's surface for billions of years. Since the moon doesn't have an atmosphere or magnetic field, it collects solar particles directly, including helium-3, which gets trapped in tiny dust grains. It's estimated that just 1 ton of helium-3 could provide the same energy as 10 million barrels of oil in fusion reactions. Unlike traditional nuclear fuels, helium-3 fusion doesn't create harmful neutron radiation, making it a clean energy source. However, no reactor is currently capable of using helium-3 in fusion processes. The growing interest in helium-3 comes from its potential for future energy technologies. Helium-3 concentration on the moon depends on the region. Areas with more exposure to solar wind and finer soil grains tend to have higher concentrations. Apollo mission samples found measurable amounts in different parts of the moon, including both Highlands and Maria. The highest concentrations are expected near the moon's equator, where the sunlight and solar wind are the most direct. To extract helium-3, scientists would need to mine and heat the lunar soil, a process that requires temperatures of about 600 degrees. Since helium-3 isn't chemically bonded to the soil, it can be separated by controlled heating and filtration. The challenge is that large amounts of soil would be needed to obtain useful amounts of helium-3. Even so, its energy density makes it worth the effort. Several countries, including China and the US, are interested in studying helium-3. NASA and private companies are already modelling ways to extract it using robotic systems. Although commercial extraction isn't feasible yet, helium-3 has strategic importance for space exploration. It's one of the few resources that justifies large-scale lunar mining for energy. In controlled lab conditions, helium-3 can fuse with deuterium to release energy without activating reactor materials, unlike regular nuclear fusion. This reaction is clean, and the byproducts are easier to manage, making it an appealing option for future reactors. Many research projects are exploring helium-3 as a future energy source. On Earth, helium-3 can be obtained from tritium decay, often in nuclear reactors or weapons. However, this source is limited and highly regulated. The Moon, however, has vast natural reserves of helium-3, which makes it an attractive resource for future energy needs. Some experts call it the oil of the Moon, even though practical use remains speculative. Helium-3 is also valuable in fields like cryogenics, neutron detection, and MRI systems, making it useful even in small amounts. While the idea of lunar mining is exciting, there are environmental concerns. The Moon's surface is delicate, and any excavation could damage its structure and the scientific records preserved in the soil. The long-term impact of removing solar-deposited elements is still unknown, so careful planning and international regulation would be required. Robotic missions could help map out where the highest concentrations of helium-3 are located, helping to assess the environmental impact and feasibility of mining. Lunar missions, such as NASA's upcoming rovers and India's Chandrayaan mission, are expected to help gather this crucial data. Mapping helium-3 distributions would make future mining efforts more targeted and environmentally responsible. The Moon's helium-3 reserves represent a major untapped energy source, and studying it could provide insights that go beyond scientific exploration, helping to shape the future of energy on Earth. The Moon also contains minerals that don't naturally occur on Earth. Some of these minerals are entirely unknown to us and formed due to the unique conditions of the lunar surface, such as its low gravity and lack of atmosphere. Without weathering or erosion, lunar rocks preserve structures that would quickly break down on Earth. These stable minerals, such as armicolite and tranquilite, provide a rare look into the conditions of non-Earth environments. These minerals can help scientists understand how rocks evolve without the influence of water, weather, or biological activity. In addition, some lunar minerals have high concentrations of titanium and iron, which are rare on Earth. These minerals offer valuable insight into the Moon's volcanic history and may also contribute to future space exploration efforts. These differences affect how the minerals react when exposed to heat and pressure. Ilmenite, for example, is crucial for future technologies that could extract oxygen because it contains oxygen atoms. Understanding how it behaves on the Moon could help us better use resources there. The Moon is also home to strange glass-like materials. These include volcanic glasses created when lava cools quickly, and impact glasses formed when meteorites hit the surface. Some of these glasses contain tiny iron particles, a feature that is rare on Earth. Their magnetic and optical properties are important for space science. Each impact and eruption on the Moon captures a moment of extreme energy. Minerals that trap solar wind particles add to the Moon's uniqueness. Some grains contain hydrogen and helium from the Sun, trapped over billions of years. This is something Earth can't replicate as our atmosphere blocks solar particles. The Moon, however, has been exposed to solar winds for billions of years, trapping solar ions in its surface soil. These elements offer clues about solar activity over time. As technology improves, scientists are finding new minerals in lunar samples. Some minerals form under extreme conditions and are preserved due to the Moon's unchanging environment. Some of these crystals are tiny but reveal details about the inner workings of planets and their cooling processes. The discovery of these minerals helps us understand how factors like gravity, heat, and material composition shape the geology of planets. The Moon's minerals are also useful in materials engineering. Some minerals that form under intense heat could inspire new synthetic materials. They may have special properties, such as resistance to damage, unique magnetic behavior, or better heat conduction, which scientists are studying. Though these minerals are rare, their qualities make them valuable in many fields. The Moon's surface is slowly shrinking as it cools over time. This cooling causes the solid crust to compress, creating stress on the surface. Unlike Earth, which relieves this stress through tectonic plates, the Moon lacks this system. Instead, the surface forms fault lines where the crust pushes over itself. These features, called lobate scarps, can stretch for miles. NASA's Lunar Reconnaissance Orbiter has spotted hundreds of these scarps on the Moon, some as high as 30 meters. These scarps are well preserved and show that they formed recently in geological terms. Since the Moon has no atmosphere, these features remain intact for millions of years. The rate of shrinkage is slow but noticeable. Scientists estimate that the Moon's diameter has decreased by about 50 meters over the last few 100 million years. While this change is small, it's enough to cause noticeable deformation. The scarps suggest that the Moon is still experiencing internal changes, even though it appears quiet. Seismometers left by the Apollo missions recorded shallow moonquakes, which are linked to this process. These quakes sometimes reached magnitudes near 5 on the Richter scale and occurred near the surface. The pattern of these quakes matches the areas where scarps are located, further linking the Moon's cooling with tectonic activity. Some of these quakes happen during the Moon's morning when the surface rapidly heats after a long night. This temperature change can reach over 250 degrees, causing stress along the crust, especially at fault lines. The combination of cooling and thermal expansion causes the deformation seen in the scarps. These scarps tend to appear near the edges of large ancient lava plains called maria, which have thinner crusts and are more susceptible to deformation. Some scarps also cut through craters, showing that they formed after these impacts. This suggests that the moon's contraction is still happening, not just a relic of the past. Unlike Earth, the moon's tectonic features are not part of vast plate boundaries but are isolated due to its small size and single-layer crust. However, the presence of these scarps proves that the moon's interior is still evolving. The moon is not geologically dead as once thought. Even though changes are subtle and slow, the landscape continues to shift over time. The scarps influence how the moon's surface material or regolith collects and how small landslides happen. Steep slopes don't accumulate as much dust, and new fractures disturb existing layers. These changes may impact the preservation of materials, including solar wind deposits. Scientists also study the scarps to learn more about the stress inside the moon. Mapping these features provides clues about the strength and properties of the lunar crust. Future missions may use scarps as areas to place instruments for studying moonquakes. By monitoring these quakes over time, scientists can refine their models of the moon's interior structure. This helps determine the size of the core, the composition of the mantle, and the moon's thermal history. It also allows scientists to track whether the contraction of the moon is speeding up. A shift in the moon's temperature could increase stress on the surface, leading to more active deformation. The formation of scarps suggests that the moon's cooling is ongoing. Heat continues to escape from its interior, causing the moon to shrink. This contrasts with planets like Mercury, which show more extreme shrinkage. The young fault lines on the moon suggest that internal heat may last longer than previously expected, especially in localized areas beneath the crust. This shrinking process could affect future lunar bases. Scarps may create seismic hazards or slope instability in certain areas. Engineers will need to take these factors into account when choosing construction sites, especially in regions near fault lines or areas that have recently deformed. Long-term geological stability is crucial for any permanent settlement on the moon. The moon's scarps serve as visible evidence that its crust is still changing. Even without plate tectonics, the moon's surface is slowly being reshaped by internal forces. The heat trapped inside the moon continues to circulate beneath its surface, even after billions of years. This residual heat comes from the decay of radioactive elements and from the impacts that occurred early in the moon's history. Although the surface experiences extreme temperature changes daily, the deeper layers remain more stable. Even so, subtle thermal waves can be detected beneath the surface. During the Apollo missions, astronauts installed heat probes into the lunar regolith. These probes measured temperature changes several meters below the surface, showing that heat was still moving upward from deeper layers. More recent missions, like China's Chang'e landers, have confirmed these findings. Temperature sensors detected variations in heat that couldn't be explained by surface effects alone. Some regions retained more heat than others, hinting at differences in the composition of the subsurface. For example, basaltic rocks retain heat longer than lighter rocks like anorthosite. This difference in heat retention reflects the layering beneath the moon's crust. The crust is thinner on the near side of the moon, especially under the large lava plains known as maria. These areas may still have pockets of warmth beneath them, which could explain the slow and uneven flow of heat from inside the moon. This thermal activity is important for understanding how the moon's surface and subsurface are still changing. It shows that despite billions of years of cooling, the moon's interior is not fully dormant. Even in what seems like a stable environment, small processes are constantly shaping the moon's surface. These processes show that time, temperature, and material composition are still active. Instruments have found that rocks buried deep within the moon respond slowly to changes in temperature. Heat takes time to travel through or escape from these rocks, which leads to delayed changes in temperature. This delay creates wave-like patterns in the temperature data that move through the surface seasonally and even yearly. Over millions of years, these waves carry energy from the moon's interior to the surface. The continued flow of energy shows that the moon is still cooling. Radioactive elements like uranium, thorium, and potassium-40 create heat inside the moon. These elements are concentrated more in certain highland areas, especially on the far side of the moon. These isotopes decay slowly and release energy over billions of years. Areas with more of these elements show slightly higher heat levels, which can be detected by orbiting instruments. Studying how heat moves through the Moon helps scientists learn about its internal structure. It also helps us understand how other planets and moons cool. The Moon acts as a perfect laboratory for studying long-term thermal changes. Future missions plan to place more advanced instruments below the surface to track heat over longer periods and at deeper levels. This will help refine our models of radioactive decay and the Moon's crust. By studying heat, scientists can trace ancient volcanic activity and cooling processes. Even small temperature changes provide valuable insights into the Moon's geology. Although the Moon's thermal activity is slow, it leaves measurable clues. Every change in temperature, earthquake, and mineral alteration tells part of the story. Even though there are no active lava flows, the Moon still has heat beneath its surface, which continues to push energy outward steadily. The Moon also gives off its own infrared radiation, not just sunlight. While we often think of the Moon as simply reflecting the sun's light, it also releases its own energy in the form of thermal infrared radiation. This infrared light isn't visible to the human eye, but special instruments can detect it. This radiation gives us a detailed map of the Moon's surface temperature and provides insight into its material composition and energy balance. The heat is absorbed during the lunar day, and as the surface cools, it releases energy back into space. The highest emission of heat occurs after noon, when surface temperatures are at their peak. Unlike visible light, infrared radiation depends on the thermal properties of the materials. Different minerals release heat at different speeds, creating contrasts in infrared images. These variations help scientists identify rock types and textures on the Moon's surface. For example, basaltic plains retain heat longer and glow brighter in infrared light, while areas made of anthracite cool faster. This difference in how materials cool creates distinct thermal patterns across the surface. Infrared data also shows how the surface reacts to the Moon's extreme temperature changes. During the long, cold lunar night, the surface cools quickly but not evenly. Some rocks hold on to heat longer and glow faintly in the infrared, continuing to release heat hours after sunset. Dust and regolith, moon dust, behave differently depending on their grain size and compactness. These factors affect how long a region emits detectable heat. NASA's Lunar Reconnaissance Orbiter has instruments that track this thermal glow, including the Diviner radiometer, which measures temperature changes across the entire surface. This data helps us understand the thermal inertia of different materials or how resistant they are to temperature changes. One of the most important uses of infrared data is to detect new impact sites. Fresh craters tend to retain heat longer than the surrounding terrain, making them easier to spot from space. Infrared images also reveal features like lava tubes, caves, and voids beneath the surface, as these areas trap heat differently than the open ground. Some regions emit more infrared radiation than expected, which has puzzled researchers. Certain magnetic anomalies are linked to these warmer areas, suggesting there could be subsurface interactions. Differences in the Moon's surface composition or buried ice may also explain these unusual thermal readings. Scientists are continuing to study these variations to figure out their causes. Even the poles of the Moon emit low levels of infrared radiation, despite never receiving direct sunlight. These areas maintain extremely cold temperatures close to absolute zero, but thermal instruments can still detect faint emissions. Understanding these cold zones is important for planning future lunar missions. The Moon's infrared radiation also affects how quickly equipment like rovers and landers cool down. As they lose heat to the environment, understanding the local temperature emissions helps engineers design better thermal control systems. This ensures that instruments can survive the extreme temperature shifts of the lunar night and protects electronics from the deep cold of space. The Moon's infrared glow can also change over time. Small events like micrometeorite impacts or solar radiation can disturb the regolith and alter how it absorbs and emits heat. Monitoring these changes helps scientists track how the Moon's surface is slowly evolving. Long-term observations show how the Moon's surface is constantly transforming. Scientists use the Moon's thermal data to better understand other airless bodies in space such as asteroids and other moons. The Moon acts as a baseline for comparing how other planets and moons behave thermally. The Moon doesn't just reflect sunlight, it radiates its own silent energy. This invisible glow helps us understand how heat moves, how rocks behave, and how a seemingly lifeless world is still changing. Through infrared data, we see that the Moon's surface is alive with thermal activity, even though it may appear still to the naked eye. Some lunar craters may also contain ancient ice, preserved in permanently shadowed regions near the Moon's poles. These areas never see sunlight due to the Moon's tilt. Inside certain craters, the temperature is so stable that ice can remain there for billions of years. NASA's L-Cross mission and India's Chandrayaan missions have detected signs of hydrogen in these regions, suggesting the presence of ancient ice. This ice likely came from comets or solar wind interactions. Over time, these materials accumulated in the cold traps of polar craters, where they remain untouched. Unlike Earth, the Moon has no atmosphere or magnetic field to move heat around, so once ice settles in these cold areas, it stays there. The lack of geological activity on the Moon further protects these ice deposits. Instruments like neutron spectrometers and infrared sensors have confirmed elevated hydrogen levels, which indicates the presence of water ice. In 2009, the LC-ROSS mission even found water ice mixed with other compounds like methane and ammonia in the Cabus crater. The ice on the Moon isn't evenly distributed. Some craters have large amounts of ice, while others only have traces. Factors like slope, depth, and the history of impacts influence how much ice is stored in each crater. The most promising areas for future missions are near the South Pole, particularly Shackleton and Shoemaker craters. These regions are now primary targets for exploration. In addition to water ice, these shadowed regions may also hold other compounds, such as carbon-based molecules and sulfur, which could provide more clues about the Moon's history and its interactions with comets and solar winds. This ice has been preserved for billions of years, acting as a time capsule that could provide valuable information about the early solar system. Unlike Earth's surface ice, the Moon's ice is mixed with soil and rock, making it harder to extract. New techniques, such as using microwave energy to release the ice from the soil, may help scientists access this frozen resource. Advanced drilling and heating techniques will also be needed. Scientists are already using thermal models to predict the age of these ice deposits, with some estimates suggesting they may be over 2 billion years old.